Okay, so our today's class is about hybridization. Hybridization. Now, simply, let's discuss about what is hybridization. Hybridization, you know that what is an orbital. Okay, orbital, inside an atom, we have shells. Inside the shells, there are subshells. Inside the subshells, there are more subdivisions which we call the orbitals. Like this is one orbital, this is one orbital, these are all orbitals. And inside the orbitals, there are what? There are electrons. Like this is an electron, this is an electron, this is an electron, this is an electron. These are all electrons. Okay, so orbitals are the innermost subdivision of a shell. First, a shell is subdivided into subshell, then subshells are further subdivided into orbitals, then inside the orbitals we have the electrons. Okay, now there are different shape for different orbitals. Like we have s orbital, we have p orbital, we have d orbital, and we have f orbital. So for AS level, we just need to know the shape of S and P. S orbital has got a spherical shape, the nucleus is there, and P orbital has got what we call the dumbbell shape, or it's an H shape, and in the middle there is the nucleus. Okay, so these are all the subshells. Okay, so in the S subshell there is only one orbital. In the p subshell there are 3 orbitals. In the d subshell there are 5 orbitals, and in the f subshell there are 7 orbitals, and each of these orbitals, they contain electrons. Okay, for example, the 3 of the p orbitals, like one of the orbital, so one of the p orbital is along the x-axis, like we would call it px. The nucleus is here, like this. Okay, then another p orbital is along the y-axis, and we call it py. Okay, here is the nucleus, and another p orbital is along the z-axis. For example, this is the z-axis, and we call it pz. All right. Okay, now what happens is that before an atom forms bonds, it undergoes the process of hybridization. Now what is hybridization? What is hybridization? Hybridization is okay. Hybridization is like there is an outermost shell of an atom. Okay, so in the outermost shell there are also orbitals. Present. So what happens is that just before the atoms of outermost shell, the outermost shell of atom, they form covalent bond with another atom. What happens is that in the outermost shell, all the orbitals of the outermost shell, they undergo the process of mixing. Orbitals mix together. Okay, orbitals mix together to form a set of same number of set of same number of new orbitals. Okay, so before mixing and after mixing, and after mixing, the number of orbitals remains the same number of new orbitals. Okay, so how many types of hybridization are there? Okay, let's see. There are many different types of hybridization. For example, consider that in an outermost shell, there is a S subshell containing one orbital. There is a P subshell that contains 3 orbitals, and there is a D subshell that contains 5 orbitals, and so on. Okay, now if this happens is that one S and one P orbital mixes, then what we will have, so here, okay, so let me draw it separately. One S and one P orbitals mix, we call it sp hybridization. Okay, now if this happens is that one S and 2 of the P orbitals mix, we call it sp2 hybridization. This 2 refers to the fact that 2 orbitals are being mixed. All right. Okay, now if this happens that 1s and 3 p orbitals mix, we will call it as sp3 hybridization. Okay, now if 1s and 4 and 3 p orbitals and 1 d orbital mix, we will call it sp3d hybridization. Okay, all right. Now the thing is that why is the hybridization occurring? How many new orbitals will form? Okay, for example, if 1s and 1p mixes, we call it sp hybridization. So how many orbitals are mixed together? 1, 2. So 1s and 1p is being mixed. All right. Okay, let me draw P with red color. 1s and 1p orbital is being mixed. All right. Okay, so here 1, 2 orbitals are being mixed. So what will happen is that we will get 2 new orbitals, and each of them we will name as sp. Since 2 orbitals are being mixed, so 2 new orbitals will be formed, and each of them will be named as sp. Now if this happens is that 1s and 2 p orbitals mix, then so here 3 orbitals are mixing, so we will get a set of 3 new orbitals, and each of them will be named as sp2. Okay, that is the case. Okay, so why is the hybridization needed? Okay, hybridization is needed because you know that bonding occurs when the orbitals overlap. Okay, so this is one orbital, this is one orbital, so these are 2 p orbitals. So p orbitals are overlapping here. Like, let me give you another example. This is s orbital, this is then this is p orbital, so we would call it a sp overlap. Okay, now when the orbitals overlap, the fact is that different orbitals have different energy, and in different orbitals they have different energy means. For example, talk about s orbital, and talk about, for example, px orbital. That means the p orbital along the x-axis, which would look like this. Okay. Okay. So, for example, there is an electron in the s orbital. There is an electron in the p orbital. Look, the thing is that the energy of s orbital is less than energy of p orbitals, and it is further less than the energy of d orbitals. So when when different orbitals mix, the electrons within them, what do we mean by the energy of orbitals is actually the kinetic energy of electron inside the orbitals. Okay, so what happens is that if the electrons of different kinetic energies, they mix together, then what happens is that the overlapping that is occurring, the overlapping that will occur here will be very much unstable because of different kinetic energies or variable kinetic energies of the electrons. Okay, so if the orbital overlapping occurs with s remaining as s and p remaining as p, then different covalent bonds, or the electrons inside different covalent bonds, will all have different very much different kinetic energies that would make the bonds unstable as well as the overall molecule unstable. So what happens is that these orbitals all together, they undergo the process of mixing, so that all the new set of orbitals, they all have the same electrons. They all have the electrons of same kinetic energy. Okay, so they mix together so that the kinetic energy of electrons gets distributed, and then all the electrons, they have the same kinetic energy, and it looks like this. For example, this is an s orbital charge, and the electron inside the s orbital has got an energy of 20 joule, say, for example. Okay, so this is sorry okay, so this is the nucleus, and this is a p orbital in which the electron has got an energy of 60 joule. Okay, so this is an s orbital and this is a p orbital. Okay, so what happens is that after the mixing occurs, for example, we are getting a set of orbitals that would possibly, or for example, that would look like this. So this is one orbital, nucleus in the middle, and this is another orbital, the nucleus in the middle, although the shape looks awkward, but I have nothing to say. So there is an electron inside. So these two electrons now will have the average kinetic energy of the 60 and 20, that means 40. That means both the electrons are now having the same energy of 40 joule. Now if the orbitals overlap in this state, then the electrons vibrating inside the covalent bonds or moving inside the covalent bonds will all have the same energy, and the covalent bond will be quite stable. But if the electrons would have overlapped in this state, that means the very different kinetic energy of electrons, then the covalent bonds would be very much unstable because of different vibration energy of the electrons in different covalent bond. So that's actually the need of hybridization. Okay, that's why, since the hybridized orbitals, inside the hybridized orbitals, the electrons have the same energy, so they will form the same energy covalent bonds. So when hybridized orbitals they overlap with each other, forming covalent bonds. The bonds are really very strong, and the bonds are really very strong and is very stable. We call these bonds sigma bonds. That means when the hybridized orbitals overlap, or the s orbitals overlap anywhere, we call that bond a sigma bond, which is very strong. But if other than s there are any unhybridized orbitals that overlap, for example, we have one s and 3p anywhere, for example. So here are 4 orbitals, isn't it? So these 3 orbitals mix to form 3 new set of orbitals, and all of which we will be naming as sp2, and one p orbital which is unhybridized. So these 3 orbitals, these 3 hybridized orbitals will overlap to form a covalent bond known as the sigma covalent bond, and this orbital is still unhybridized. It is not it didn't mix up during hybridization. So this orbital will also form a covalent bond, but that will be weak because the electron inside this orbital has got a large amount of kinetic energy. So the electrons will be vibrating with large kinetic energy and would cause the bond, covalent bond, to become weak. So this electron in this unhybridized orbital will have a high kinetic energy. So the bond formed by this p orbital, will be weak. When unhybridized orbitals forms bond, we call them pi bond. Okay. So that is the sigma bond and the pi bond, and these pi bonds are very weak. Okay. Now, what is the privilege of forming sigma bonds and pi bonds? Okay. So an atom will always first form a sigma bond. Okay, not this way. For example, between atoms A and B. Okay, listen very carefully. Between two atoms, there will always be a sigma bond at first. There is always one sigma bond, and it is always one between two atoms. I am mentioning it again and again that it is between two atoms. And if now more bonds form between the two atoms, then these bonds will be the pi bonds. Looking at pink. Okay. So for example, AB, there is only one bond, so that bond must be, this must be sigma bond. This is the symbol for sigma. And if you say that no, there is a double bond between the two atoms, then okay, then only one bond is still sigma and the other bond will be pi bond. If you say that no, there is a triple bond, so one bond will be sigma and the other two bonds will be pi bonds. Okay. So between two atoms, always one sigma bond is formed and rest of the bonds are pi bonds. Okay. Now, how to calculate how to determine the hybridization around an atom? Like if I say that, for example, ammonia NH3, and there is a lone pair of electron. So if I say that what is the nature of hybridization in the outermost shell of this nitrogen atom, is it sp, sp2, sp3, or what it is? Okay. So if structures are given, then it's quite easy to find a number which we are calling it as the hybridization number or the steric number. Okay, so hybridization number will be equal to number of number of sigma bonds plus number of lone pairs. Pi bonds are not counted here. So hybridization number will be equal to number of sigma bonds and number of lone pairs. All right. Okay, that's the lone pair. So you know that when a single bond is present, it is always sigma. So between two atoms there will always be just one sigma bond. Okay, one sigma bond. Between two atoms there will always be one sigma bond. Okay, now how does hybridization number is related to the nature of hybridization? Okay, if hybridization number is 2, it can be 2, it can be 3, it can be 4, it can be 5, it can be 6, etc., etc. Even it can also be 1. Okay, now let me give some arrows with a different color. 1, 2, sorry. Okay, if hybridization number is 1, then if hybridization number is 1, then it would be, then it would be just S. So there is S only. So if the hybridization number is 2, then it would be Sp. Okay, so the nature of hybridization is Sp. 2 means there are 2 orbitals being overlapped. 3, so 3 orbitals are overlapping. Just remember again, these are all the hybridization numbers. Okay, this is 3, so 3 orbitals are overlapping. So that means that this is 1 s and 2 p's, a total 3 orbitals, which means Sp3. All right. Okay, 4 means 4 orbitals are overlapping. 1s and 3, sorry, it is Sp2. So 1s and 3 p orbitals are overlapping, so we will call it as Sp3. If the hybridization number is 5, that means 5 orbitals are overlapping, so Sp that is 4 and D, that would give you Sp3D. Okay, so this is how, by finding the hybridization number, you can tell the nature of hybridization in the outermost shell of an atom. Okay, let's look at some examples. Let's start with ammonia. Okay, so first find the hybridization number, and hybridization number in this case is, look, we have 1, 2, 3 sigma bonds, and we have 1 lone pair. So 3 sigma bonds plus 1 lone pair, that would give us 4. The hybridization number is 4, and hybridization number 4 means the nature of hybridization is Sp3 in the nitrogen. All right. Okay, so what's happening is that in the outermost shell of nitrogen, we have 3 p orbitals and 1 s orbitals mixed together to form the hybridization, and then forming these covalent bonds. Okay, now let's look at another example. For example, I'm telling it's carbon. Okay, so you are asked to find the nature of hybridization of this carbon atom. Okay, so first count the hybridization number. Okay, so how many sigma bonds are here? Here is 1, here is 2, here is 3. So here there is a double bond, isn't it? So one bond is sigma and another bond is pi. So there are 3. So there are 1, 2 and 3 sigma bonds and no lone pairs are there. So hybridization number would be 3 sigma bonds and no lone pairs. That means hybridization number is 3. So the nature of hybridization around this carbon atom is sp2. Okay, I hope you have got it. So this is how hybridization number can help you to find the nature of hybridization around in the outermost shell of each atom. Okay, let me give another example. Okay, this is the structure of sulfuric acid. My question is this sulfur atom is sp3 hybrid, the outermost shell. In the outermost shell of the sulfur atom, the nature of hybridization is sp3. How? Okay, that is my question. Okay. So our next content is so hybridization is done. Now next bonds are formed. So you know that covalent bonds are formed by what process? By simply the overlapping of orbitals in the outermost shell of the atoms. Okay. So these are the electrons. So now what happens after the orbitals overlap? The orbitals overlap and the electrons are paired up. What happens after that? Let's see. Now this is really too easy to understand. That look, for example, these are the electrons, isn't it? The overlapped electrons. Okay, so what is the charge of electron? You know, electrons are negative charge, isn't it? And these, what about this nucleus? All these nucleus are positive charge. All right, so what happens next is that the already overlapped electrons are attracted by the nuclei or the nucleus of the participating atoms. Okay, so these electrons are attracted by the nuclei of atoms. So the electrons, what happens that the electrons starts to vibrate to and fro like this. Okay, the electron doesn't remain in this position, it starts to vibrate in a to and fro manner like this. Why? Because of the attraction of the nuclei of atoms. So the electrons start to vibrate to and fro. Okay, now this this power of attraction of the electrons, so this attraction, the power of attraction of the nucleus on the bonding electrons, that means the force or the power by which the nucleus attracts the bonding electrons is what we call the electronegativity. Okay, So the force or the power by which the electrons, the force or the power by which the bonding electrons are attracted towards the nuclei of the participating atoms, or attracted by the nuclei of the participating atoms, is known as electronegativity. That means if an atom has higher electronegativity, it means that the power of attraction is greater. For example, if I say that okay, this is the s orbital, and okay, this is another s orbital. Okay, these are the s orbitals and these are the electrons. So the electrons now will be attracted to the nucleus because of the attraction of the nucleus. Now if I say that this atom has got a higher electronegativity, that means this nucleus has got a greater power of attraction. Okay, so what will happen is that these electrons, these bonding electrons, will still vibrate to and fro, but the amount of vibration will not stay in the middle between the two atoms. Instead it will slightly shift towards this atom. So the vibration, for example, suppose this is atom A and this is atom B. So here is atom A and here is atom B, and just imagine that these are the these are the bonding electrons. So if A and B had the same electronegativity, so what would happen is that, look, the distance traveled by these electrons towards B will be equal to the distance traveled by electrons towards A. That means the vibration range would be same, like this, from the mid position. Okay, but here what are we saying? That B has a higher electronegativity. So what is actually going to happen is that this is A, this is B. Since B has a higher electronegativity, so what would happen is that these electrons will vibrate more towards B and very less towards A. Okay, so we express this case in the following manner, that we draw A and B and draw these bonding electrons slightly more towards B rather than drawing in the middle. Rather than drawing in the middle. Okay, so this refers to the fact that B has a higher electronegativity. So the electrons are shifted slightly towards B, and we know, and you know, that electrons are negative charged. So the thing towards which electron goes or shift becomes negative. So in this case the electrons are slightly shifted. Slightly has the symbol of this, slightly shifted towards B. So B will now be slightly negative, and since the electrons are shifted slightly away from A, so we will call A as slightly positive. And so this covalent bond has got two atoms of slightly positive and slightly negative polarity because of the difference difference in electronegativity between atoms A and B. So we will call this covalent bond as a polar covalent bond. But if the electronegativity difference was very less, or they had the same electronegativity, like in this case, then what would happen is that A and B, the electrons would get as much as close to A as much as it goes close to B, because they have almost the same electronegativity. So what would happen is that this bond would not be a permanent dipole. There would not be a permanent dipole because there is no permanent shifting. Okay, it remains on average in the middle, which is not the fact in this case. Okay, so what happens here is that, look, sometimes this A gets slightly positive and B gets slightly negative when the electrons are shifted towards B, and when after one cycle the electron goes towards A, then A becomes slightly negative and B becomes slightly positive. So what happens is that, look, slightly positive negative, the overall positive and negative, they are cancelled out. All right, so here dipole is created same as in this case, but in this case the dipole was permanent. Okay, look, I'm circling. But in this case the dipole was what? The dipole was permanent. But in this case the dipoles are not permanent. So, and still the dipoles cancels out. So we will call this covalent bond as a non-polar covalent bond or temporary dipolar covalent bond. Okay, and we will call this as a polar permanent dipolar covalent bond or dipolar covalent bond, or simply polar covalent bond. And this is what? This is the non-polar covalent bond. All right. Okay, so now what happens if the difference in electronegativity is very large? Let's see. And this is our last content for today. Okay, for example, this is one atom, and I am considering both S. So this is an SS overlap. All right. Okay, so these are the electrons in the bond. These are the electrons in the bond. Barely I can see it. Okay, these are the electrons in the bond. Now let's consider that okay, so let's consider that, sorry, that this atom has got a higher electronegativity. I'm calling it as atom B. This is atom A. So atom B has got a higher electronegativity, very high, very high electronegativity than atom A. So what happens is that these electrons are extremely attracted by atom B rather than atom A, which applies a very weak attraction force. So what happens ultimately is that all these electrons will get entirely into atom B. That means atom B will take all electrons from atom A, like this. Okay, So what's happening? It's that A has become positive charge and B has become negative charge. Now there will be an electrostatic force of attraction between the two atoms, which we are calling it as the ionic bond. Okay, so the atoms has now turned into ions. That means if the difference in electronegativity between the two atoms is very large, then the higher electronegative atom will take all the electrons away permanently, forming a complete negative charge on it and making the other atom completely positive, and that creates the ionic bond. So first of all, a covalent bond is created. Then, due to difference in electronegativity, the covalent bond might stay as covalent bond, or it may turn into an ionic bond. Or if it remains as covalent bond, it may remain as nonpolar covalent bond, or temporary dipole covalent bond, or a permanent dipolar covalent bond. Okay, so let me give you an electronegativity scale. No, let's keep it as suspense. We will deal about the electronegativity values, E values. Then we will look at del E values in our next classes. Alright, okay, that's all for today. Thank you guys, thank you very much. Please comment all your problems in the comment section below this video, and I will try to solve it one by one. Okay, thank you, goodbye.